Welcome back to session 25 on beams. This is the third portion. And in this final part, we're going to discuss how we might treat beams as springs. And this treatment of springs, or treating a structure as a spring, should be familiar because we did this with bars. We treated them as springs. In fact, before we knew what an elastic modulus was, and the K equals EA over L formula, right? What we discussed is the scaling of the spring constants associated with bars and how they scaled with diameter and how they scaled with with length and how we could make use of these scaling parameters to calculate out new spring constants for bars that were under tension. We also discussed how we could think of these configurations as putting a bar, for example, in series with itself if we double its length, like you see here. And we discussed how we could think of putting the springs in parallel when we were adding or creating a larger cross-sectional area. Okay, so if we half the length of the bar, also, okay, the spring constant would double. If we double the cross-sectional area of the bar, that's kind of like putting a couple of these springs in parallel with each other, and that could also double the effective spring coefficient for this new bar with twice the cross-sectional area. Okay, so this idea of being able to scale the spring constant according to the dimensions of the bar was and is a useful technique. We also discussed in some detail the Hooke's law and springs in series, springs in parallel, which we discussed. We also discussed how sometimes Hooke's law is given as a negative kx or a positive kx, and it depends whether you're thinking about the force in the spring or the force that you're using to pull on the spring. Okay, and again, when we think about springs in parallel, we think of them potentially getting stronger and stronger. Okay, and we think of them being added to each other. Okay, like this. So K parallel here is K1 plus K2. And when we think of springs in series, as I put more and more of these springs in series with each other, it becomes easier and easier to get displacement. And so it actually makes things less stiff as you put more springs in series with each other. And the relation there is 1 over the effective spring constant is equal to the summation of the inverses of the individual spring constants, as you see here. Or if you have just 2 springs, you can say K1, K2 over K1 plus K2. And in session 8, we then discussed how we could connect these properties in a bar to the material property of elastic modulus, but we also need to know something about the cross-sectional area and also the length. Okay, so we've discussed how we could use this integration integral form, okay, of an internal force, area, and elastic modulus along a beam to get our famous pli formula. Okay, and so that is what we see, and this is dx here. Just it got cut off, right? Because I didn't paste in as carefully as I probably should have. So if I'm thinking about the change in distance between B and A here, the displacement between them, we integrate this equation out with a constant P and a constant A, and we get pli, or PL over EA. And if we are doing this carefully, we should make sure that this is the internal load, but often we just think of it as the external load. And if we're thinking about it as an external load, it's fine to say that P equals K delta, because this external load is the same as this internal load, and K is equal to P over delta, and that's got a spring constant of EA over L. So that's for a bar. And so this is a little bit of a review. Okay, now let's talk about beams. So how do you calculate the spring constant for a beam? Well, you look at the expressions relating the displacement. Okay, so this would be like our V that we normally use, and force, P, right? And you say, okay, P over the displacement is going to give me K, right? And it's important to pick the appropriate location. Okay, so if we're at the end of the beam over here, okay, then it's pretty straightforward. We say that the displacement is PL cubed over 3EI. And, we're not being super careful about the direction of the sign here, okay, for these displacements, because, typically we say, okay, V is equal to this, so it's, or V is in the positive Y direction, and so then this would be negative, right? Again, are you going to pull, or are you thinking about the force inside the spring? All right, so P equals K delta, or KV in this situation, and so we can say that the spring constant is just going to be this denominator divided by L cubed. All right, and it has a similar property to what we saw with the axial loading of a bar and those spring constants, right? If I make the length longer, then it means that the spring constant goes down. It goes with L cubed though, so it's significant. If I use a material with a higher Young's modulus, the K goes up. Okay, that's also what you see. And so instead of EA over L, now we have an I. And so if I change the cross-sectional profile, right, not the area as in a bar, but EI is related to area, right, then if I increase the I, we're able to increase the K as well. Okay, so that's the basic idea, right, of how you can model a spring as a cantilever. What did I say? A beam as a spring. So we have an example here. Here's a beam with this configuration now that we're getting a little bit familiar with. And we say that P is equal to K delta. Okay, that's the form we want. We say, okay, we're interested in this deflection, okay, given at the middle. So again, using just a positive value, although it might be negative, right? So be careful with the sign conventions. But this is our V at L over 2. Our delta is equal to PL cubed over 48 EI, which is what we have here. Or if you were to plug it in here, you would get the same thing. If you plug in L over 2, that is. And we get that P over delta is equal to 48 EI over L cubed, denominator divided by the numerator without the P. And that's the K. That's pretty much it. Okay. Now, I'm going to do a question here to wrap up this session. And it's going to be using or making use of creating a relationship for a cantilevered beam and its spring coefficient, and then it's put on an actual spring. Maybe this is maybe it's a bar, I don't know, but it's something that has a K. And so this is an indeterminate system, right? Because I could, if I remove this, I would go right to a determinate system with just P on this cantilever, right? So sometimes, again, we saw this in the past too, that if it's an indeterminate system, one approach is to start thinking in terms of spring constants or spring coefficients, which then can make it easier to do some algebra and solve, okay, for forces that might be unknown or displacements, pretty much, and then go back and look at the unknown forces or unknown moment, if you like. All right. So To conclude this session, what we've discussed is the displacement or deflection of beams. And we've discussed how we can use superposition as a tool, okay, to calculate unknown reaction forces or just displacements for a determinate system, because the forces and moments should be known for a determinate system. But if it's an indeterminate system, we can also use superposition, right? Indeterminacy, right? The degree of indeterminacy, again, using superposition to solve these types of problems, forces, deflections. And we also shouldn't forget that we can also go back and use the relationships, the EI, second derivative of v with respect to x equals moment. Okay, we can use it and then integrate, so we can use the method of integration for solving these indeterminate problems. But those are kind of the two techniques: integration and superposition for solving indeterminate systems or indeterminate beams. And we can think of using, actually, I guess there's a third, because we can also use beams as springs. Okay, and then we could also attack these indeterminate systems, as we show with this final question, number 4. All right. Well, thank you very much. And if you have any questions, please feel free to contact me. Have a good day.